This video will introduce you to atomic structure visually by showing you a series of 2D images that represent ground state elements. Before we can look at the images, I will introduce the way the shells, subshells, and orbitals will be represented in 2 dimensions. We will look at the 3D projections of these orbitals to get some understanding of what the 2D images represent. Then we will look at the images for all atoms of the current periodic table. It might be helpful to have a periodic table handy to refer to when viewing this video. Here you see the 4 shapes and colors that will be used to represent the 4 kinds of subshells, S, P, D, and F. The nucleus will be represented by a small black dot at the center of each atom. The blue S subshell is spherically shaped in 3 dimensions, so it's nicely modeled in 2D with a circle. A blue circle represents 1 orbital and can hold up to 2 electrons. The pair of purple triangles represents the P subshell. A pair of purple triangles represents 3 orbitals and can hold 6 electrons. The 3 p orbitals are called px, py, and pz and are oriented in 3D, as we will see on the next slide. The purple triangles represent all 3. Similarly, the yellow square represents the D subshell. A yellow square represents 5 orbitals and can hold 10 electrons. The 5D orbitals are called dxy, dyz, dxz, dz squared, and dx squared minus y squared. The yellow square represents all 5. The green star will represent the F subshell with 7 orbitals and can hold 14 electrons. The 7 F orbitals have designations as well, but they are complicated and not important for our purposes. Now let's look at the 3D models that correspond to each of the subshells. Here you can see the orientation of the 3 p orbitals in 3D space. They are each shown on their own set of axes, but in reality, they all exist in the same space with the same center. The 2D purple triangles represents these 3 p orbitals. Here you can see the 5 D orbitals in 3D space. They are shown on their own set of axes, but in reality, they all exist in the same space with the same center. The 2D yellow square represents these 5 orbitals. Here's what the 7 F orbitals look like. The green star represents all 7. Once again, they exist in the same space with the same center. In addition, all S, P, D, and F orbitals exist in the same space with the same center. Now that we know how the 4 kinds of subshells will be represented in our 2D model, we are ready to see how the primary shell size will be demonstrated. We will begin building our atoms first by looking at what subshells will be available at each of the primary shell levels. We start with the nucleus and then the n equals 1 shell, which only has an s orbital. The n equals 2 shell that has both s and p, and the n equals 3 shell that has s, p, and d. Starting with the n equals 4 shell, we have access to all 4 kinds of subshells. N equals 5 similarly has all 4 kinds. But the n equals 6 shell, as far as we know with our current periodic table, uses only S, P, and D. And n equals 7 has only S and P. That exhausts the shells we need to describe all currently known elements. There is no n equals 8 shell that we know of in reality. We can certainly calculate an n equals 8 shell, as well as D and F shells for higher n values, but they don't correspond to reality. Notice that the size of all types of subshells increases with the primary shell. The primary shell is the biggest determining factor for how large an atom is. That's its n value. Its n value determines how big an atom is. The other thing to keep in mind is that just like the orbitals for each subshell, though these shells are drawn separately, in reality they share the same space and same center. We are now ready to look at the 2D models for each of the elements. We'll start with hydrogen. The ground state image for hydrogen shows the nucleus and the 1s orbital or subshell. The s subshell is the only one that can be called both an orbital and a subshell because that subshell has only one orbital. Hydrogen has only one electron in the 1s orbital, so its electron configuration is 1s1. As we move through the periodic table and look at the ground state image for each element, the ground state will depend on how many electrons each element has. Even though the hydrogen atom has only one electron, the atomic structure available to the electron includes all shells, subshells, and orbitals. Indeed, it is from the model of hydrogen that we know what the shells and subshells look like. All atoms have roughly the same internal atomic structure. All have all 7 shells available to use, but most often they will live in the ground state and use the lowest energy orbitals possible. That is called the Aufbau principle. These 2D images will show you the ground state of each element with the upper empty shells stripped away. Let's complete the ground state picture for helium. It looks the same as for hydrogen. The only difference is that now the orbital holds 2 electrons. Lithium and beryllium use the 1s and 2s subshells. The electron configuration for lithium is 1s2, 2s1, and beryllium is 1s2, 2s2. Often we refer to the electron configuration of an element by just indicating the highest energy electron, with the understanding that any lower energy position will also be filled by other electrons. The next subshell to fill is the p subshell, and that completes the second period of the periodic table. Notice that the 2p orbital extends a bit beyond the 2s orbital. When we move to the 3s image, you see that the 3s orbital is larger than the 2p subshell triangles. Moving to 3p, we again have a p subshell that extends beyond the s. That completes the third period. Notice that for all of our ground state images, the outer edge is either an s or p subshell at all times. Those are the valence electrons that are available to react with other atoms. Here's 4s. Again, the 4s orbital is larger than the 3p triangles. With the fourth period, we get the first transition metal block that is represented by our first d subshell, the 3d subshell. You can see the yellow square forming inside the atom and is not readily available for reaction, even though they are the highest energy electrons. Next comes the 4p. If you look carefully, as the shading of the purples, you can still see the 2p and 3p subshells within the atom. That completes the fourth period. Moving to the fifth period, it's the same kind of process as we saw with the fourth period. 5s surrounds the outermost P subshell. We get a second inner square, and then the largest P triangle yet. One last thing to notice on this slide before we move on is the nucleus. See how it is relatively easy to see the nucleus in the first image here, but is almost completely obscured in the last image. This trend will continue in all the future images. Period 6 starts out just like period 4 and 5, with the 6s orbital. But then it jumps back down to the 4f subshell. You have to look carefully to see the 4f star shape that's smaller than the outer valence subshells. Remember, f orbitals come in 7 different varieties and can hold 14 electrons. This corresponds to the ground state electron configuration for the 14 elements, the lanthanides. The remainder of the sixth period completes just like the fourth and fifth period did. There's a third square added for the third row of the transition metals, including gold, and it finishes with a large P subshell. The seventh period feels just like the sixth. A large s orbital followed by a second green star for the 14 actinides, including uranium. The 10 elements represented by the 6d subshell and the 6 for the final 7p subshell have been observed at least once, but are not naturally occurring. Many have not even been named yet. And that completes the seventh period, and it's the last of our 2D images. I want to conclude this video with some observations and assumptions about the whole presentation. Most of these 2D atoms look generally like a blue circle and a pair of purple triangles. And that pretty much matches what we see in reality. All atoms look pretty much the same, and they have valence electrons that are located in their highest principal shell in the s and p orbitals of that highest principal shell. The nucleus is difficult to see in the larger atom figures. This is also a good representation of reality because the inner shell electrons shield the nucleus from the outside electrons. So the outside electrons don't really know that there's a nucleus down there in the middle. The third point here, the 2D figures assume that the orbitals that result from many electron systems, like all the elements beyond hydrogen, are identical to those that can be calculated for the hydrogen atom. Well, that's an assumption that is present in the quantum mechanical model itself. It's not just a limitation for these 2D models, but for any quantum mechanics. And the last comment, the 2D figures assume that the size of the orbitals increases in size linearly. Well, that may or may not be true. You can see the linear scaling of all the shapes because the spaces between nested shapes is the same from level to level. I hope these 2D images have helped you to develop an understanding of the inner structure of atoms, the way they fill, and the relationship between the atomic structure and the periodic table.